So how about full fidelity audio? How do I get the human hearing range? What would the sampling rate be for that? And what does that even mean? And what should a bit depth be? It's kind of a measurement of, we're talking about quantization, how we store the samples. We need enough bits to be able to store these numeric values, the sampling rate. They work hand in hand. So the answer really is you want the most of each category. You want the highest sampling rate and the highest bit depth possible. And you'll see why in just a second. You could get really technical at this. This is beyond my scope. Harold Nyquist was a scientist at Bell Labs, and he came up with a theorem, a 28-page theorem, as to why we need the sampling rate that we need. And it turns out the magic number is the human hearing range times 2 with a little bit of extra padding. I'll talk about in a second, to reconstruct it. So let's see what that means. We know the hearing range goes up to about 20,000 hertz, the ideal human hearing range. And for, again, the 28-page theorem why, and working with his team, somebody decided to need a little extra in there. Let's make it 22,050. And just go on faith with me here, 22,050. So we want that hearing range with a little padding, and we're going to multiply it by 2 because you got to think about the compression and rarefaction, right? Those positive and negative values. So if you need 22,050 times 2, that's 44,100 samples per second. And it's called the Nyquist theorem. Think of this as positive 22,050 and minus 22,050 on that number system we were just showing you. All right. Those are the measure. That's a measurement of hertz, cycles per second. So you actually need 16 bits if you want the human hearing range recorded without any sort of noise or glitches or problems. All right. And if you have 16 bits, you can get a number, you get a really big number. We're talking 32,768 at the top, all right, on the 16th bit. And if you were to add all these together, you would come up with a number like 65,535. Throw in a 0 and it's 65,536. We don't need that much. But 15 bits isn't enough. See, it's only 16,384. So we need to have a value that can store 44,100, and that happens to be the 16th bit. All right. And that's why you always hear, oh, that's 16-bit, 44,100 samples per second audio. That's what we're talking about. All right. Now, it's very important. All the stuff I just told you, I'm going to sum up in another way. The lower the sampling rate, we know we need a high sampling rate, what we perceive as high, 44,100 samples for the human hearing range. Now, if you subtract from that, you're going to lower the possible frequency range that you're going to hear because the high values are going away first. Imagine if I took, less samples per second. Now I only need to have them represented. I'm going to only do 4,096 samples per second or something like that. So my frequency range is being severely limited. Okay, and it doesn't take long for this to start to just really roll off. We can cheat a bit though, and back in the day when it was a costly thing real estate wise on a CD or a cartridge or something like that, if you had dialogue, we can get rid of a lot of the high frequencies because that speech range is really the most important frequency range, and that tends to be more of a mid-rangey kind of thing, like in the 2K to 5K area. So we could get rid of a lot of the high end, basically make a lower sampling rate and get away with it and save space. Nowadays, we don't have to worry as much about that sort of thing, but it's important to know the history behind it. So lower sampling rate means lower frequency range. If you lower the bit depth, this is how we store it, right? How many, think of these little containers we're storing, right? This is the process of quantization, storing these values. And we lower the bit depth, the less accurate, or what I like to call the less smoothness you will have here, where you really have kind of this very noisy, artifacty, distorted kind of quality to the audio, just because of the nature of how we're storing it electronically. We're losing the clarity and kind of the I can't even talk, granularity of the sample. So it's a bit more blocky, and you have this kind of noisy experience. The reason for that is, I use this horrible 3-bit example again. You have this big blocky wave here, right? If I were to listen to this, it would be agony. But if it was 8 bits or 16 bits, let's say it's 8 bits, I'd still have a problem because I'm seeing these blocks here. And if you listen back, you're missing out on some of the curvatures of the audio signal coming in. So what needs to happen is we need to smooth those out somehow. And this is done by, it's actually done by a process called Gaussian noise distribution, but what we need to know is it's just dithering or smoothing out electronically some of these values before our ears ever hear it. Unfortunately, that means we're introducing noise as kind of a mask or kind of a buffer to smooth out these rough edges. And so you're going to notice this more on like 8-bit audio. If you listen to old 8-bit audio files from an old PC game or something, you may hear that they're very hissy kind of sounding or a little fuzzy, and that's the noise that has to be introduced by dithering to kind of smooth out these rough edges. And you won't hear that on 16-bit audio, good 16-bit audio. Okay, so these are introducing errors and glitches. Okay, sometimes we call them artifacts. Okay, and this is what I just mentioned. It's adding a small amount of noise to the audio. Sometimes it's a more than a small amount, depending on the actual bit depth. Okay, so now our ears are about to hear this, and so we're going to play it back and convert it to analog. All right, this digital to analog conversion is known as a DA converter. Oftentimes, it's just a single circuit in an audio interface. It's a DA converter. It has to be very precise. All right. And once again, there's a process to kind of smooth out and restore the original audio signal. Again, it's beyond the scope of this introductory course. All we need to know is that in addition to the dithering process, there are some other electronic elements within the DA converter that ensure that there won't be any really bad pops, clicks, glitches, and things like that, producing transient peaks that may really hurt your ears, like really screechy stuff. Okay, and it happens. If there's a corrupt file you're trying to play back, the DA converter should be smart enough to tamp down any of those really, really glitchy sounds.